So today I would like to continue the topic of thermodynamics. I will start with adiabatic change and adiabatic process. Then I would like to show how the pressure is related to the quantity we defined in the last lecture using the maximum entropy principle for equilibrium states. Next, I will move on to the mechanical work and heat. And at last, I will discuss three thermodynamics potentials: enthalpy, Helmholtz free energy, and Gibbs free energy. In the previous lecture, we briefly considered the volume of a thermodynamic system. We turn to this now in more detail. In general, the external boundary of a thermodynamic system is of physical significance since it confines molecules. In a certain sense, this boundary may be regarded as a confining external potential. By its nature, this wall is not statistical, but is simply prescribed. A system may interact with its surroundings by changing the wall location. If the system interacts with the environment only through movements in the wall and not through molecules inside and outside exchanging energy, then the system is referred to as thermally isolated. Since the wall in such a system is not statistical, it has effectively zero entropy. Further, since there is no direct molecular interaction with the outside, the principle of increasing entropy with time holds for thermally isolated systems as well as closed systems. Suppose we can specify the confinement using one parameter lambda, an example of which is volume, and suppose the system is in thermal equilibrium if this parameter is not changing. Now, the rate of change of entropy with time ds over dt is a function of the time rate of change of the external parameter d lambda over dt. If we assume that this latter change is small, then we can perform a Taylor expansion of the former in terms of the latter. The constant term is 0, since d lambda over dt equals 0, implies a system in equilibrium, so entropy does not change. The next linear term must also be 0, since changes in lambda can occur in the opposite direction, meaning this linear term reverses sign. However, ds over dt is greater than or equal to 0 for changes either way. Thus, to leading order, we must have ds over dt is approximately equal to a times d lambda over dt squared, which may be rearranged to ds over d lambda approximately equals a times d lambda over dt. Thus, as the change in the wall occurs at a slower and slower rate with time, the rate of change of entropy with the external parameter also approaches 0, and the entropy does not change with the wall variation. Such a very slow change in a thermally isolated system is known as an adiabatic change and is also termed reversible, since entropy is not changing as the system configuration is changing. Conversely, changes in which the entropy increases are termed irreversible, because the second law means they clearly cannot occur in reverse. An adiabatic change is one in which the change in the mechanical parameter lambda is much slower than the thermal equilibrium time. As the mechanical change proceeds, then the system at any time may be regarded as very close to thermal equilibrium. In practice, this is not really a severe condition or restriction, and many processes of practical interest are very close to adiabatic. For example, if a piston is moving outward, and so the volume of the gas within it is increasing, then it may be shown that providing the velocity of the piston lead is much less than the speed of sound, then the change is very close to adiabatic. The thermodynamic energy, E, for an adiabatic process is the mean of the actual energy of many different systems in the same state of thermal equilibrium. Energy E for an adiabatic process equals the mean of the energy of an arbitrary system with external parameter lambda. We are assuming that this system is in a thermal state of equilibrium and hence has a Gibbs distribution. Remember that the form of this distribution will depend on lambda, since this parameter restricts the possible values for the position of molecules. Now, in any system governed by Hamiltonian dynamics, we have dA over dt equals partial derivative of A with respect to t plus the Poisson bracket of A and Hamiltonian H. In general, the energy and Hamiltonian have a zero Poisson bracket, which means that d of pq lambda over dt equals partial derivative of E of pq lambda with respect to t, and equals partial derivative of E of pq lambda with respect to lambda times d lambda over dt. Taking an ensemble average with respect to the appropriate Gibbs distribution, we obtain dE over dt equals the mean of dE over pq lambda over dt, and equals the mean of the partial derivative of E of pq lambda with respect to lambda times d lambda over dt. Consider now an adiabatic change for a system, which means that entropy is conserved. The time rate of change of thermodynamic energy as lambda changes is given by d over dt equals the partial derivative of the thermodynamic energy E with respect to lambda times d lambda over dt. Note that if the entropy were to change in a non-adiabatic process, then an additional term would appear in this equation involving the time rate of change of entropy. Thus, we obtain by comparing the above equations that the partial derivative of the thermodynamic energy E with respect to lambda equals the mean of the partial derivative of the total energy for a particular microstate of the system with external parameter lambda with respect to lambda. It enables a thermodynamic calculation of an important equilibrium ensemble mean, the right-hand side. For a given body of arbitrary shape in thermal equilibrium, we have seen that both the thermodynamic energy E and the entropy S are additive quantities, in the sense that if we divide up the system into a series of subsystems all in thermal equilibrium with the same temperature, then the total energy and entropy is the sum of these quantities for each subsystem. From this, we deduce that these important quantities depend only on the total volume of the system and not on its particular shape, since the system could be rearranged so that the total energy and entropy are unaffected. The thermodynamic system may thus be specified by energy E, entropy S, and volume V. And since in general there is a relation between these three variables, and two of them suffice to specify the thermodynamic state. Consider now a piston in which the external parameter lambda is the position of the moving end, and that changes are made adiabatically. That means the entropy is conserved. Changes in the volume of the gas in this system are given by the piston cross-sectional area A times change of the position of the moving end lambda. Now, if the piston's end changes position, it does so under a force due to the pressure of the gas. If the end moves counter to the pressure P, then energy is added to the gas in the piston, whereas if it moves in the same direction, it expands, then the gas does work on the piston's end and energy is lost. These energy amounts are the force exerted by the pressure multiplied by the distance traveled by a piston's end. It follows then that for an infinitesimal change in lambda, that we have pressure P times the piston cross-sectional area A equals force F, and that equals minus partial derivative of the total energy for a particular microstate of the system with external parameter lambda with respect to lambda. Averaging over the appropriate Gibbs ensemble, which is appropriate since we are considering an adiabatic change only, we obtain that the mean of force equals minus mean of the partial derivative of the total energy for a particular microstate of the system with respect to lambda equals minus partial derivative of the thermodynamic energy E with respect to lambda. The mean pressure on the surface of the piston's end equals minus partial derivative of the thermodynamic energy E with respect to the volume V. Now, when we defined temperature in the previous lecture, we assumed the volume of the body V was constant as the thermodynamic equilibrium was achieved. In other words, temperature T equals the partial derivative of the thermodynamic energy E with respect to the entropy S. It follows from the property of differentials and two last equations that dE equals T times ds minus P times dV, which is a fundamental relation of thermodynamics. In the last lecture, we defined the quantity using the maximum entropy principle for equilibrium states. As we saw, we had the partial derivative of energy E with respect to the volume V equals constant between two bodies concerned. We can write that ds equals 1 over T times dE plus P over T times dV. So we have the partial derivative of entropy S with respect to the volume V equals pressure P over temperature T. The constant quantity between two bodies in equilibrium is just the quotient of their pressure and temperature, as we anticipated earlier. We have now given a physical meaning to the P, previously identified as the pressure of the two bodies on each other. This illustrates the power of the maximum entropy principle in identifying relevant thermodynamic variables. As we noted earlier, as a practical matter, when two bodies equilibrate, their pressures will equalize generally much more rapidly than will their temperatures. Thus, mechanical equilibrium is generally much more rapid than thermal equilibrium. As noted earlier, as the walls of a system change, mechanical work is done either by a system on its environment or by the environment on the system. By convention, work is positive if done on the system. The work W is done by the pressure acting on an area of the walls of the piston. We have, therefore, dW equals minus mean force times d lambda and equals minus pressure times dV. If the body is thermally isolated, then by conservation of energy, this work changes the total energy E of the system by the same amount. If the system is not thermally isolated, then the two things may not coincide since the internal energy of the system may change as a result of a molecular interaction with the environment. We can therefore write the change in energy as the change in work plus heat energy equals heat energy minus pressure times the change in volume. Now, if this interacting system is internally in thermal equilibrium, but it may not be with its environment, then we can use equation on the change of energy and the last equation to deduce that the heat energy equals temperature times change of entropy. It should be noted that we have defined only infinitesimal differences of work and heat, and in fact, if one considers two different trajectories of a system within thermodynamic space, that is specified by two of energy, entropy, and volume, for which both trajectories have the same endpoints and starting points, then the amount of work and heat added will be path dependent. Of course, the total energy added will only depend on the starting and ending points, since it is specified by the state. Given the path dependence of these quantities, it makes no sense to refer to the heat energy or mechanical energy of a system, because only differences make sense. Note also that in all previous considerations, the bodies concerned are assumed to be in thermal equilibrium. If this is not the case during a thermodynamic process, then equation dq equals T times ds must be modified to dq is less than T times ds, since entropy may increase independently of the addition of external molecular energy, that is heat energy. As was mentioned in the previous section, it is possible to specify the thermodynamic state using volume, entropy, and energy, and further there exists in general a functional relationship between these three variables, which means that two will suffice. Now, this functional relationship may be written as energy is a function of entropy and volume. And from this, we can deduce pressure by differentiating partially with respect to V, and temperature, but differentiating partially with respect to S. Thus, this functional relationship will determine all thermodynamic variables of interest. This situation leads to the terminology that energy E is a thermodynamic potential when expressed via this equation, since the gradient vector gives the other variables. It is possible to construct other thermodynamic potentials in other ways. If the pressure P is held constant during a thermodynamic process, then we have the additional energy dq equals d of energy E plus pressure P times volume V, and that is identical to dH, where H is referred to as the enthalpy, and is identical to energy E plus pressure P times volume V. The enthalpy represents the heat energy added to a system held at constant pressure. For a more general process, we have dH equals dE plus P times dV plus V times dP. By combining these equations, we obtain dH equals T times ds plus V times dP, and hence that the temperature T equals the partial derivative of enthalpy H with respect to the entropy S, and the volume V equals the partial derivative of enthalpy H with respect to the pressure P. Thus, enthalpy H of PS is also a thermodynamic potential from which T and V can be determined by partial differentiation. Suppose now we hold the temperature fixed as we alter the thermodynamic state. We have then that the work done is given by dE minus dQ, and because dQ equals T times ds, we obtain d of E minus T times S, that is identical to dF, where F is the Helmholtz free energy. And this Helmholtz free energy is identical to energy minus temperature times entropy. Helmholtz free energy represents the mechanical work done during isothermal change, and in a similar fashion to the previous potential, we have dF equals dE minus T times ds minus S times dt. And by combining these equations, we obtain dF equals minus S times dt minus P times dV. And hence that the entropy S equals minus derivative of Helmholtz free energy F with respect to the temperature T. And the pressure P equals minus partial derivative of Helmholtz free energy F with respect to the volume V. Thus, we identify a third thermodynamic potential, F of TV. A potential called the Gibbs free energy can also be defined using the pressure and temperature, the variables that arise from the Lagrange multipliers of the previously mentioned maximum entropy principles. Thus, we write G is identical to E minus T times S plus P times V equals F plus P times V equals H minus T times S. And this is because F equals E minus T times S and H equals E plus P times V. We can derive that dG equals minus entropy times change in temperature plus volume times change in pressure. And hence that the entropy S equals minus partial derivative of Gibbs free energy G with respect to the temperature T. And the volume V equals the partial derivative of Gibbs free energy G with respect to the pressure P. Hence, G of PT is a fourth thermodynamic potential. Thank you.